Dear students, today's topic is the RC oscillator, or very popularly known also as RC phase shift oscillator. The code of this topic is ELEC-OSC-S3A. This is a typical block diagram of the oscillator, where three-stage RC circuits are used, RNC1, RNC2, RNC3, and the output signal is obtained. And the main feature of this circuit RC phase shift of the three cascaded circuits is that they produce total of the 180-degree phase shift with a suitable, obviously, connected components, which is C and R. It produces 60 degree phase shift each, and 3 in total. 3 into 60 is 180-degree. RC oscillator use a combination of an amplifier and RC feedback network to produce the output oscillations due to the phase shift between the stages. In the amplifier tutorials, we saw that the single stage transistor amplifier can produce 180-degree phase shift between its output and the input signals when connected as a common emitter amplifier, and that is output signal across the collector load depends entirely on the input signal injected into the transistor base terminal. But we can configure transistor stages to operate as an oscillator by placing resistor capacitor RC network around the transistor to provide the required regenerative feedback without the need of for a tank circuit. In this circuit, we don't use the tank, the LC tank circuit. Only RC tank circuit will be RC circuits will be used. Components will be used. The frequency selective RC coupled amplifier circuits are easily to build and can be made to oscillate at any desired frequency by selecting the appropriate values of resistance and capacitance. For an RC oscillator to sustain its oscillations indefinitely, sufficient feedback of the correct phase, that is positive in phase feedback, regenerative feedback, must be provided along with the voltage gain of the single transistor amplifier being used to inject the adequate loop gain into the closed loop circuit in order to maintain oscillations, allowing it to oscillate continuously at the selected frequency. This is a typical block diagram of the RC phase shift oscillator. This is the typical amplifier having input and output. This is the feedback network, which includes the three-stage RC network as well. The output is taken here from the output. A portion is taken and fed to this output signal is fed to the feedback network, which produces a phase shift of the 180-degree and is fed back to the input. The output out of phase by 180-degree, so when it comes from the output, again it is brought in phase with the output. Both signal become the input, the signal which is coming from this feedback network. So this description is given in this paragraph. You can read it out. That is very clearly mentioned. These diagrams or the figures illustrates very nicely the phase shift. This is one particular RC circuit, and we provide a zero phase suppose input signal. What it does, it makes the output signal out of phase by 60-degree, which depends upon the value of the R and C. So 60-degree, that doesn't mean that each and every RC circuit will be producing 60-degree. You can control the phase. This is, we also call it a phase generator circuit, because we can change by changing the value of R and C, we can have the change in the phase at the output. And you have done one experiment also in the phase generator when we are measuring the phases, and we have used this RC circuit as a phase generator. So in detail we have discussed over there, but again we are quickly going through for those as well who are viewing this lecture or watching this lecture. So 60-degree phase shift, one single circuit is producing. So here we have got three circuits. This is first, this is second, this is third. C1, C2, C3, R1, R2, R3. In this case, since each is producing 60-degree phase shift, so all these C1, C2, C1 is equal to C2 is equal to C3, R1 is equal to R2 is equal to R3. But in case, suppose we might have 20-degree, one is generating, the other one is, let's say, 80-degree, then some other is maybe generating some other, and but the sum is 180-degree. We might have, in that case, C1, C2, C3 will have different values. So the total is output. This is the typical phase diagram you can see for single stage, and this is for the three stage. Very clearly self-explanatory. You can see that here is the phase shift of the 60-degree for the, this is the output, which is the we get the the input and the output is, they are creating 60-degree. So this is the typical. So this has the input with the 0 and the output with the 60-degree. This is the total 90-degree, but and so on. The phase is being 60-degree. Phase shift is being produced at the output. And here the typical, the total of the, all of these three, the input is 0, the output is now 180-degree. This is a 180-degree phase shift if we take both the signals. Now the RC phase angle, we would like to discuss the phase angle. If you see the typical, these RC in series, the circuits are connected. One typical circuit, it has the XC is equal to 1 over 2 pi FC, and if you take the total impedance, which is R, a magnitude of the impedance is R square plus XC whole square, and the phi angle is tangent inverse of Y by X, or the the imaginary part divided by the real part, which is the XC over R, where XC is the capacitive reactance of the capacitor, R is the resistance of the resistor, and F is the frequency. In our simple example above, the values of R and C have been chosen at the required frequency. The output voltage leads to the input voltage by an angle of about 60-degree. Then the phase shift angle between the each successive RC section increases by another 60-degree, and giving a phase difference of between the input and the output 180-degree. So as shown by the following vector diagram. This vector diagram typically shows that the input voltage is having 0 phase. The VC1 produces first phase 60-degree, the second 60-degree, and the third VC2 and VC3, then it aligns along the 180-degree phase shift to the input. So the output is, that is the total of all these three voltages at VC3 that creates or generates 180-degree phase shift. So this is written in this description. You can read it, and the similar the information is given. Now let us take the basic RC oscillator circuit. You can see this is a typical amplifier which we have at the input. 3-stage RC circuits are connected. This is the self bias common emitter amplifier. We take a small portion from from the output signal, put it in this 3-stage RC circuit, which also does the sampling network as well. Small portion is then taken, which is the, you see the signal which is being coming out of phase. This is the with the starting with 0, it becomes out of phase and fed it in input, and which is again taken across the output. Now one particular thing I would like to mention here, that you don't see the tank circuit here. So how does the oscillations are produced? So actually what happens that in this particular type of the oscillators, we do not use the LC tank the component. They are typically in fact are using the oscillations of the QPoint in the load line. We have discussed that quite at large during the amplification. So let me demonstrate that this is a typical load line of the common emitter amplifier circuit. This is VCC and this is IC. This is VCEQ. This is a Q point. Q point means a quiet point or quiescent point, and this is ICQ. This is the supposed to be the Q point where the transistor is biased and supposed to be staying at the middle. This is a class A amplifier. You can see it is in the middle of the load line. So this is DC load line. When AC signal is fed into from the base, this is the base, particular base, then at the output we get the typical AC amplified signal. So if you remember, we discussed that, and for the newcomers who are studying this topic, we have three zones, three regions in the output characteristics curve. One is called the saturation. This one, the first saturation region. This is the cutoff region, which is we call it it is the zero. Basically, this is not the cutoff region. This is very close to the let me draw the line so you can have idea about it. Again, so this is a typical where the we can see that the IB is there. This is IB, actually this whole IB is 0 at this particular point. This is the cutoff region. This is due to the minority charge carriers, and the ultimate job of the engineer or the scientist is to when the production of the transistor you are making, keep this region as low as possible. So this is because of the minority charge carriers, unwanted, uninvited charge carriers, as you know, due to temperature or the various other factors, we might have this or the heating effect inside, or the excessive current is flowing through the transistor. This region may go up and down because of generation of since the transistor is made from the crystal, germanium or silicon. Its intrinsic property is that at the room temperature, the electron hole pairs are continuously generated. Recombination and generation is going on with the temperature. So what the scientists do, normally in normal amplifier, class amplifier, it is supposed to be not varying. Q point, we suppose that it is fixed, it is not going up or down, but it's in practically Q point is oscillating a little bit, but small. So if the oscillation is very small, that can be ignored, but should not be very large for the normal amplifier. But in case of the phase shift oscillator, what we do is that we intentionally make this the transistor such that with the temperature it brings the disturbance in the Q point. It agitates the Q point, that is the little bit the minority charge carriers are being generated, and Q point oscillates up and down. Now these the small oscillations are fed back and they are amplified. So that is a typical main cause of the oscillatory the oscillatory phenomena inside the RC phase shift oscillator. We call it noise in technical language. That this is the noise of the transistor. It could be due to fluctuation of the DC. We can make that DC should be bringing some fluctuations which causes the Q point go up and down, and that is fed back to the input. Okay, we are back now. So those fluctuations from these transistors are fed back, and those oscillations are amplified, and going on this amplification are received at the output. So all description is given in this circuit, in this paragraph as well as in this paragraph. So what we are now looking for the resonant frequency. Resonant frequency, the typical frequency of that RC circuit is given by 1 over 2 pi RC 2n square root, where Fr is the oscillator's output frequency, R is the feedback resistance in ohms, and C is the fedback capacitance in farad, N is the number of RC feedback stages. This is the frequency now at which the phase shift circuit oscillates in our simple example above. So we have this So the frequency that in our simple example above, the number of stages is given as n. N is the 2 times the n, which is, if there are 3 circuits then 3, if there are 4 then 4, and all together that number is included. Since the resistor capacitor combination in the RC oscillator ladder network also acts, ladder means the steps you take, one first step, second step, third step of the 3 circuits, also acts as an attenuator, mean reduction, the signal is decaying because of the damping, that is the signal reduces by some amount, it passes through the each passive stage. It could be assumed that the 3 phase shift sections are independent of each other, but it's not the case, as the total cumulative feedback attenuation becomes minus 1 by 29th times of the this beta gain, which is equal to minus 1 by 29. So the across all the 3 stages, this is the typical practical observed value. Thus the voltage gain of the amplifier must be sufficiently high enough to overcome these passive RC losses. Clearly then, in order to produce the total gain of minus 1 in our 3-stage RC network above, amplifier gain must be equal to or greater than 29 to compensate the attenuation of the RC network. With this we reach to the end of the topic. There are the operation amplifier which is not relevant, not in your course. You can read it out if you want to, and we are almost at the end of the topic, so we completed that topic, and hope that you will now study further and work it out all the details of the RC phase shift oscillator. Thank you.